Good morning, friends. So, in this lecture, we will continue with the moving curved plate. In the previous lecture, we have taken a moving flat plate held normally and we calculated what is the force, what is the work done. Similarly, we have considered a moving inclined plate and calculated what is the force, what is the work done. And we compared both the fixed plate and moving plate in both the cases, and we have shown how the force varies and how the work done varies in both the cases. In today's lecture, we will go for the third case, that is force exerted by a jet on a symmetrical moving plate, or the moving plate you can call it as a vane, but the jet is striking at the center of the vane. So this is the thing. In such a case, how you proceed? We will do first force, then work done, and I will show you some more thing also in this. And I take you to the logical conclusion why we are studying this entire impact of free jets. So we are now entering slowly one after the other into the practical aspects. Even now, we have not entered the practical application of free jets. All these piecemeal studies, plate stationary, vane stationary, plate moving, vane moving, are all basically and to give all we are studying to get an understanding of how to calculate the forces. But this is not the thing that is going to be applied practically. So we are now slowly moving towards it as and when we are going much deeper into this chapter. So straight away we go into the case and derive the equations. So today's lecture is case 3. What is that case 3? Force exerted by a jet on a symmetrical moving curved plate or vane where the jet striking at the center. So I draw the figure and I will take you forward. Suppose this is the vane. Now this is the center line. This is the direction of jet also. Now as this is moving with a velocity u, after some time this will be in this position. The jet which is leaving here with a velocity v now has to overcome the plate or the vane and strike the thing. So how it leaves? The jet leaves tangentially. So that means if you draw a tangent here and a tangent here, it makes an angle of theta here. And this angle we call it as deflection angle. And the deflection angle means it is 180 minus theta. The jet while going in this direction is now turned actually tangentially and moving like this. So that is what we are telling. So now again, jet, what is the velocity of jet? Velocity of jet, I mean absolute velocity of jet. Absolute velocity of jet is equal to V. What is the velocity of vane? Velocity of vane is equal to U. That is the area of jet. Area of jet is A, which you can calculate by pi d square by 4, where d is the diameter of jet. So what is the effective velocity of jet? Effective velocity of jet striking the vane is equal to V minus U. And what is the mass of fluid striking per second is equal to rho A into V minus U. Then what is the initial velocity of jet? Initial velocity of jet. Initial velocity of jet means effective velocity of jet. Effective velocity of jet in x direction is equal to V minus U. After striking, the jet leaves tangentially. Therefore, final velocity of jet, that means effective velocity in the same x direction, is equal to minus of minus V minus U cos theta, because this is how it leaves V. So V minus U. So what is it? This is V minus U cos theta. And this is V minus U sin theta. Therefore, applying impulse momentum equation, applying impulse momentum equation, force in x direction is equal to mass striking per second initial velocity in x direction minus final velocity in x direction. Therefore, Fx is equal to rho A into V minus U into V minus U minus of minus V minus U cos theta. So Fx is equal to rho A into V minus U whole square into 1 plus cos theta. This is what we are getting actually. So once this is obtained, force is over. So then naturally our thing is, what is work done? Work done is equal to Fx into U. So it is rho A into V minus U whole square into 1 plus cos theta into U. This is number 2. This is 1. This is 2. Then once work done is nothing but actually the output from the jet.
So this is output of the jet, which is equal to rho A V minus U whole square into 1 plus cos theta into U, right? Then what is the input actually? Input is the jet, the kinetic energy of jet leaving the nozzle, leaving the nozzle, that is equal to half into mv square. So half into rho A V into V square. This is all before striking. So there is no connection between the velocity with which the jet is leaving and the plate is moving. So now what is the input means how much energy is leaving from the nozzle. That energy is nothing but the kinetic energy. So note it as 3. Therefore, what is efficiency is equal to output by input. So how much is the output, gentlemen? It is rho A into V minus U whole square into 1 plus cos theta into U divided by input is half into rho A V cube. This is the thing. So this is 4. So this is over. Then after this, I want to do some more, basically some more calculation. So this also you can simplify rho a, you can cancel it. So you can get actually V minus U whole square into 1 plus cos theta divided by half into V cube, or you can take this 2 up into the numerator. So 2U into V minus U whole square, U is B, it is there here. 2U into V minus U whole square into 1 plus cos theta divided by V cube. So this is more important and more relevant. This is what we call it as 5. So once that is done, so now what I am going to do is for a constant velocity V, constant velocity of jet V, right? And given basically angle theta, right? Both are given. Then now you see V is constant, then theta is constant. Then what is the variable? The efficiency basically is maximum if dou eta by dou u is equal to 0. Why dou u only I have written? V is a constant, that means given value, and theta is constant, given value. Both are given. And in the above efficiency equation, the only variable that I can get here is the velocity of plate or vane. So that is why I have written this. This is very, very important for maximum efficiency. So therefore, if I calculate what is dou eta by dou u, so that means dou by dou u of 2 into u into v minus u whole square into 1 plus cos theta divided by v cube. This is our basic problem. So how in that I already told basically cos theta is constant, 2 is anyhow constant, v cube is constant. If I bring this actually outside the derivative, so 2 into 1 plus cos theta divided by v cube I can bring outside into dou by dou u of u into v minus u whole square divided by u into v minus u whole square. That's all. Basically, all remaining things have come out is equal to 0. So now if I expand it u into v minus u, so now I expand it. So if I expand actually, it is 2 into 1 plus cos theta by v cube into dou by dou u of, so now u I will keep. So it is v square plus u square minus 2vu is equal to 0. So now again I expand it. So this is constant anyhow 2 plus into 1 plus cos theta by v cube into dou by dou u of it is v square into u plus u cube minus 2v into u square is equal to 0. So now I will calculate 2 into 1 plus cos theta by v cube into, so now dou by dou u of v square u, so it is directly v square, right, plus 3u square, am I right, minus 2 into 4, 4 vu is equal to 0. But remember, theta cannot be 0, v cannot be 0, so naturally, so this is dou u by dou u as 2 into 1 plus cos theta by v cube cannot be 0 because they are already constant values. Therefore, v square plus 3u square minus 4uv is equal to 0. This is what I got. So if I expand it, it is v minus u into v minus 3u is equal to 0. Suppose if I put then in that case, if v minus u is 0, then v is equal to u. If v is equal to u, then you see the equation of efficiency. If v minus u is 0, then efficiency is equal to 0. Therefore, this is not valid. So what will be valid for maximum efficiency? V minus 3u is equal to 0 or v is equal to 3u. An excellent condition. This is 6. Right? Now what I will do, I will substitute in this. So eta maximum is equal to, what is the original equation? 2 into u into v minus u whole square into 1 plus cos theta divided by v cube. That is our original equation. So I will substitute v is equal to 3u. So if I substitute 2 into u, for example, v is equal to 3u. 3u minus u is equal to 2u. 2u whole square means it is 4u square into 1 plus cos theta by v cube, and v means 3u, 3u, 3u. So 3 into 3, 9u square into 3u, that means 27u cube. So if I take it, so finally what will happen? It is 8u cubed into 1 plus cos theta by 27u cubed. So u cube, if you cancel, what is the maximum efficiency? 8 by 27 into 1 plus cos theta. This is the maximum. So for maximum efficiency, the condition is V is equal to 3U. This is one. The second one is, what is maximum efficiency is equal to 8 by 27 into 1 plus cos theta. This is the maximum. Suppose if I apply this theta, theta is equal to, if I put 90 degrees, then what is this case? This is nothing but a flat plate held normally. So in such a case, eta maximum is equal to 8 by 27 into 1 plus cos 90 degrees. So it is nothing but 8 by 27. into 100. Calculate how much you get. Approximately 30%. Check it out. Suppose if theta is equal to 0 degrees, theta is equal to 0 degree, then it is nothing but a semicircular vane. That means this is how it is. Suppose the jet strikes like this, it leaves like this. That is what I mean by this is semicircular. So in that case, actually what is eta maximum is equal to 8 by 27 into 1 plus cos 0 degrees. It is equal to 8, 16 by 27 into 100. So probably approximately 60%. So this is what I wish to tell you. Then one question I will ask at the end. Single plate or vane moving is not really a, a practical case. It is only theoretical. Is only theoretical. Why that is so theoretical? What we are talking is so theoretical. Kindly observe. Suppose in 1 second jet moves by a distance of v. Plate moves by a distance of u. As time progresses, what happens to the distance between the jet and the plate? Distance between the jet and the plate increases. Then, after some time, jet may not strike the plate at all, or jet also to be moved. Jet also to be moved, which is not practicable, feasible. Hence, all these derivations, all the above three cases are only theoretical. These cases becomes practical and application is possible only if the plate or vane is mounted on a circular wheel. That means instead of a single plate where jet is striking like this, moving, which is not practically possible. If you take a wheel And on this, if you keep number of plates, and now you strike the jet with a velocity here v, right? Now this wheel is rotating because with the thing this starts moving with a velocity u. Now actually by the time that this jet, this number one, if I take it, this is number one, two, three, four, five, six, seven, 8. If one leaves, the eighth number flat plate comes into this position, and when eighth plate leaves, the seventh plate leaves and occupy this position, and when seventh plate leaves, sixth plate, like that it is a continuously, there will be always a plate before the jet. So that is what is practical, and that application is very much useful for us. So in the next lecture we will discuss on this type, so that we will slowly closer to the practical application of this particular chapter, which we call it as impact of free jets. So there I will stop here this lecture today, and we will take up in the next lecture the series of the flat plates and series of vanes, where I will calculate, not only the forces, the force I will calculate, the work done I will calculate, the efficiency I will calculate. After the efficiency, what is the condition for maximum efficiency I will calculate, and what is the maximum efficiency I can get. All this is only a checking, a prelude for turbines and centrifugal pumps. So kindly remember that in mind. And now we go into the next class, taking up the series of plates or vanes. Before that, basically, we can do some problems also, but I complete that also the series, and then I will do the problems. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.